Let's do an example. So we're going to use the function f of x equals e to the power negative 2x squared. And we are going to analyze the second derivative of this function in the same way that we used to analyze the first derivative in the previous section. In the previous section, we were finding the intervals where it's increasing or decreasing, and all the local extremes, maxes and mins. But in this case, now we're going to find the intervals of concavity, the intervals on which it's concave up or concave down, and the inflection points, which are the points on the graph where it changes concavity. So to do this, we need to take two derivatives. So first, f prime. That's going to be, since this is e to some power, we're going to get that same thing, e to that power. But then, of course, we're going to multiply by the derivative of whatever exponent, whatever power that power was as a function of x. So in this case, the derivative of negative 2x squared is negative 4x. So that's our f prime. And now f double prime, this time taking a derivative of f prime. F prime is now a product of two functions of x. We have the exponential one, and then we have this linear function. And so we need to do the product rule on this. So first we'll do the derivative of the first thing, which is exactly what we already found, negative 2x, e to the negative 2x squared times negative 4x. So that's the derivative of the first one, times the second one, which is negative 4x again. So actually I'm just going to put squared on that, since there's two of them. And then plus the first function just by itself, not differentiated, times the derivative of the second function, which the derivative of negative 4x is just negative 4. So there's the second derivative by the product rule. So now, since we're going to try to figure out where f double prime is either 0 or undefined, in this section, it now makes sense for us to simplify this as much as we can. So I am going to simplify this by factoring out e. Actually, let's factor out 4 e to the power negative 2x squared. So I'm taking out the e to the negative 2x squared since it's in both of these. I'm also going to pull out this 4 from both of these. Let me think about this for a second. I think we should, nope, that's exactly right, perfect. And so then what we're going to have left over after factoring out is 4x squared minus 1. There we go. And that is actually a difference of squares. We can actually simplify this a little further. 4e to the negative 2x squared, and 4x squared is 2x quantity squared. And so this is actually going to be like 2x plus 1 times 2x minus 1. So there's about as far factored as we can possibly get it. And the reason that I'm factoring here instead of just like simplifying in other ways is because what we want to do is set this equal to 0 now and solve it. Also figure out when it's undefined. And for doing those things, it really helps to have it in a factored form as much as possible. So now let's find the Hilbert numbers. Figure out where the, first we'll figure out where it's undefined. So looking at this, is there ever any way that this would be undefined? Is there anything that's going to cause it to be undefined? No, right? Like there's no square roots, there's no division going on, so f double prime is never undefined. There's no logarithms, no. So we don't have to worry about that. But where is it equal to 0? F double prime equals 0 when what? Well, there's three factors, right? If you set this equal to 0, one of those three factors is going to have to be 0, right? At least one. So what if the first factor is 0? 4e to the negative 2x squared. Well, that can't actually equal 0 because 4 can't be 0. It's 4, right? And then e to the negative 2x squared can never be 0, right? Powers of e will never be 0. You can get any positive number out of that function, but never 0 itself. So that part's never going to be 0. So what about the other factors? 2x plus 1 is going to be 0 when x is negative a half. Set that equal to solve it. Set that equal to 0 and solve it, and you will find x would be negative 1/2 versus 2x minus 1 will be 0 when x is positive 1/2. So there we go. Those right there, those are our Hilbert numbers, which is just a silly way to say Hilbert. There we go. A silly way to say that those are the potential inflection points. Now we have to do a sign chart to figure out if they actually are inflection points. So the sign chart, those are the only places where it's possible where f double prime could change sign. And f double prime is defined everywhere else. So I'm going to draw a number line and plot my -1/2 and my +1/2 with a, those are both zeros, right? So I'll put solid dots. And then we're going to find some test values in between. So I'm going to grab 0 in between, -1 in this interval, and +1 in this interval. And then what you could do is go ahead and stick these numbers into the second derivative here. So the first part is always going to be positive. Even though it's e to a negative power, this is always going to give you a positive number. Okay, like e to the x is always positive, no matter what x is. So all you have to do is look at the other two factors. When x is -1, we're going to have -2 plus 1. So this is going to be negative. And then 2 times -1 will be -2 minus 1, which will also be negative. So in this, for -1, f double prime is going to be negative times negative, which is positive, actually. So that's positive second derivative on that entire interval. Now at 0, if we stick in 0 for x, we're going to have +1, positive, times -1, negative. So that's overall negative. So it's negative on that interval. And at 1, we're going to have 2 times 1 plus 1 is 3, that's positive, times 2 times 1 minus 1, which would be 1, which is also positive. Positive times positive, which is overall positive. So in this case, our signs are alternating. Remember, that doesn't always happen, but in this case it does. So here it means that both of these are going to be inflection points. Let's sum up our answer. Remember, we're trying to find intervals of concavity and inflection points. So our answer will look like this. It's concave up on the intervals -∞ to -1/2, and the interval 1/2 to infinity. Those are where it's positive. It's concave down on the interval -1/2 to 1/2, is where it's negative. And then our inflection points will occur at two x values, x equals -1/2 and x equals +1/2. Sometimes, and I can't remember how it is in WebAssign, but sometimes in some problems you're asked to find the y-coordinate as well. And if you want to find the y-coordinate as well, you should take these x coordinates and stick them back into the original function, right? Because if you're trying to find the actual point on the graph where that concavity changes, you want to know its y-coordinate, which would be given by f, not one of the derivatives, but f itself. So sometimes you may need to do that, but I mean, like if I put a question on a test or a worksheet, I usually just do it this way and ask you to find the x values.